Now that we've seen how call and return instructions work and how the stack works, I want to talk about calling conventions, which are a set of agreements that various pieces of software use about how information is going to be communicated. Now, we've already seen that the y86 uses the stack to store the return address when we make a function call. But we're also going to use the stack to transmit parameters sometimes, if we can't use registers for one reason or another. We'll also use the stack to store local variables. So these kind of agreements are contracts that different pieces of software, like the compiler and the assembler and sometimes the operating system and other language runtimes, are going to use as ways to communicate information. So for example, if you wanted to interface a high-level language like C, I know some of you don't consider that a high-level language, with assembly language, you have to know how functions in one language are going to communicate with functions in another. And the primary data structure that we use to organize this information is called a stack frame. And it turns out that there are two different ways to do stack frames, and I'm going to walk you through both of them. So what is a stack frame? It's a piece of the stack. And in this picture, what I'm showing you are two stack frames. Let's assume that we have a caller like main, and then we have a callee, i.e. the thing that main is calling, like the sum function that we saw in the video on call and return. Each of those two pieces of software, main and sum, will have their own stack frame. And the stack frame starts with the address to which that unit of computation will return. So in sum, whoever calls sum, it will return. And even main, it turns out, has a return value. So that's where the stack frame starts. And then the stack frame also contains local variables. So those are all the variables you declare local to a function. And if you're going to call another function and you want to pass parameters on the stack, that too will be part of your stack frame. So let's look at the different ways that we can represent stack frames. The first one uses no base pointer, or put another way, it uses only the stack pointer itself to describe the stack frame. So let's imagine that we're in the caller, let's say main, and what we've just done is we've now called the sum function. So you remember from the last video that when we call the sum function, we've pushed the return address onto the stack. And so that's exactly what this picture shows. Now, you've never written code to do anything other than that, but when you've used languages like C, the compiler has actually gone and done a bunch of work behind your back. And what it's done is it said, how much space does the sum function need for local variables? Once it knows that amount, in this example, I'm going to claim that it needs hex 20 bytes or 32 decimal bytes. What it does, it says, okay, I'm going to allocate room on the stack for all those local variables. And the way I'll do that is that I will decrement the stack pointer by hex 20. And I'm going to allocate those local variables in that chunk of space. And so now the stack pointer is free to be used like it would normally be used, and I have the ability to allocate space for my local variables. So this is called stack frame setup. Now what you might notice is that once you've done this, all your local variables are at offsets from the stack pointer. And that's how you would access them in the assembly language that you generate from a higher level language. If there were parameters passed from your caller, those too are on the stack. They're just a little bit further up on the stack. When you're getting ready to return from your function call, you'll notice that you can't just issue a return statement because your stack pointer is not at the position such that the return address is right at the stack pointer. So you have to undo what you did when you established the stack frame by now adding that same amount back to the stack pointer, so that when you issue the return instruction, you do in fact go back to where you were before the function was called. If in fact the caller pushed parameters onto the stack, then the caller is responsible for undoing those pushes after the return. And so in this case, what we show is that there were in fact 16 bytes or hex 10 bytes allocated to stack parameters. And so upon return from this function call, we're going to adjust the stack pointer again to compensate for those 16 bytes. So that's what stack frames look like when you're just using the stack pointer. and not a base pointer. What's a base pointer? Here we go. A base pointer is a particular register that by convention is going to keep track of our stack frames. And so what happens is when you establish a stack frame, you know that the first thing in that frame is going to be the address to which you return when you're done with this function. The very next thing is going to be the saved value of the base pointer. So let's step through a function call in a world where we're going to use base pointers to manage our stack frames. So the big box in red here is in fact the caller's stack frame. We've saved the RBP, or the base pointer. When we established this frame, we allocated the space for locals, and we have some stack parameters like we did before. And so now we've just issued a call to some other function, and we're going to walk through that function, setting up its stack frame. The first thing it's going to do is it's going to save a copy of the base pointer. And the way you can think about what happens is when you push that base pointer, what you've really done is you're creating a linked list between stack frames. And so this base pointer points to the previous stack frame. Once you've saved the value, now what you can do is you can reset the base pointer to point to the current stack frame. It used to point to the caller's stack frame. Now it's going to point to the callee's stack frame, or in this example, sum. And so what that really is we've pushed RBP to save it, and then we've moved the value that's in the stack pointer to the base pointer, so it's right there. Because remember, the next thing we're going to do is create space for local variables. And by doing that, we have to change the stack pointer. So we had to do that RR move before we allocated the space for the local variables so that the RBP is really pointing at the stack frame. This set of instructions, the IR move queue and the sub queue, is exactly what we did before to create the space for the local variables. Now, what's interesting about this setup is that you can access all your variables from this base pointer instead of the stack pointer. And what happens is that local variables are negative offsets from the base pointer, and parameters, if there are any, are positive offsets from the base pointer. So if you're reading assembly code, it actually is quite helpful as you're reading through. You can use the sign of the offsets from the base pointer to figure out whether you're accessing a parameter or a local variable. When we're done and getting ready to return, just like in the non-base pointer case, we have to undo everything we did. So the first thing we're going to do is give back the space that we allocated for local variables. That's basically the add. And now we can restore the base pointer to point to the previous stack frame so that we're now in a position where when we issue the return instruction, we'll actually end up at the right place. So we restored the base pointer by doing a popd, and now we can just do a return and we're back to our caller. So the establishment of these stack frames and how you do it and which registers you use are part of these calling conventions. Now it turns out there's a bunch of other calling conventions too. And in some sense, there's a laundry list here and you're just going to have to internalize it, but let me talk you through them. So we all know that RSP is the stack pointer, but that's really a convention. And it's the convention that the hardware dictates because push and pop and call and return assume that RSP is in fact the stack pointer. Now I said, you might want to put arguments on the stack. In fact, both the y86 and the x86 pass function call parameters and registers whenever possible. And so they allocate 6 of these registers in order to contain parameters. So if you have a function with 1 parameter, it shall be passed in RDI. That's just how it should be done. If there are 4 parameters, then the first parameter is in RDI, the second shall be in RSI, the third in RDX, the fourth in RCX. You can pass up to 6 parameters this way. What happens if you have more than 6 parameters? That's when you push them on the stack. And you're going to push them in the reverse order so that argument 7 will be the smaller offset from RBP, and argument 8 will be a slightly larger offset. One of the questions I'm going to ask you after this video is, what do you suppose you do if one of the parameters you want to pass, let's say the first parameter, is bigger than will fit in a register, how are you going to pass that to a function? The other convention with respect to calling functions is, how do you return a value? And again, by convention, the return value shall go in RAX. Okay, so those are sort of the things we set up for transmitting information. There's another piece of information that we need to make a deal with, which is, which registers does a callee get to overwrite? And so what we do is we take the register set and we divide it into two pieces. There are the registers that we call caller saved, which says, if the caller cares about the contents of this register, then the caller is responsible for saving those values because the callee is allowed to scribble all over them. And in particular, the caller saved registers are those 6 parameter registers plus R10 and R11. What this means is that if I'm main and I call a function sum and pass a value in RSI, when sum returns, I cannot make any assumptions about the value of RSI. If that value was important, then before I call sum, I better push it on the stack. And then when I return from sum, I'll pop my value off. So the registers that we use for parameters, those 6 registers at the top of the slide, as well as R10 and R11, if the caller cares what's in them, it is the caller's responsibility to save them. The flip side is that there are things called callee saved registers. In particular, the base pointer, RBX, and R12 through R14. So those are promises that the callee makes to the caller, which says, I promise that when I return, I'm going to leave the same values in those registers that you had in there. So if I want to use them, and in particular, I really do want to use the base pointer, the first thing I have to do is save the old value. Then I can use the base pointer, and then the last thing I'll do is restore the value back to the caller. So I can't give you any intuitive way to remember which are caller saved, which are callee saved. A few of them should be obvious because of how we use them, like the base pointer, like the parameter registers. But for the most part, you're just going to have to remember which ones are caller saved and which ones are callee saved and what that means.